Hey there, it's Shannon MATHCHICK Myers, and today we're looking at polar coordinates and graphs. So the polar coordinate system. Up to this point, we've been using the rectangular coordinate system to sketch graphs. Now we'll be using the polar coordinate system to sketch graphs given in polar form. This form is very useful in third semester calculus as it makes many definite integrals easier to evaluate after switching from rectangular to polar coordinates. The polar coordinate system has a fixed point, O, called the pole or origin. From this pole, an initial ray is constructed. This is called the polar axis. Each point P in the plane is assigned polar coordinates in the form r theta. R represents the directed distance from the pole to the point P, and theta is the directed angle, which is counterclockwise from the polar axis. To the segment OP. That's just a line segment. Unlike rectangular coordinates, each point in polar coordinates does not have a unique representation. Can you figure out another point in polar coordinates which would be equivalent to r theta? So if you recall, when you're dealing with these circular functions, what you have is you have angles which are coterminal with each other. And so if you just add 2 pi, you get another point that is equivalent. So 0 plus 2 pi, theta plus 2 pi, would be the same point. R comma theta plus 2 pi would be the same point as r comma theta. Now, I actually meant for this to be negative r theta. Now, when you have a negative, you need to add pi to get, because r is a direct distance, so it's not going to be negative. So when r is negative, you can rewrite this by adding pi to theta. And then you get in the right spot. So in general, the point r theta can be written as r comma theta plus 2 times n times pi, or r negative r comma theta plus 2n plus 1 to make it odd times pi, where n is any integer. The pole is represented by 0 theta, where theta is any angle. So basically, let's say we had the point, P equals to 2 pi over 4. So I'll zoom in here. You would go to count out 2 from, I'm right over here. This is me. So I'm looking at this and I'm counting out 1, 2. And then you go to around that circle to pi over 4. Isn't that kind of cool? So this point P will be right about here. Do it a little bit better. This is point P. And then if we had some point Q, we'll do this one as a negative. Let's say point Q was negative 4 comma pi over 3. What we would do is we would recognize that Q would equal to positive 4 times pi over 3 plus pi, which would give us Q equals 4 comma 4 pi over 3. So I would go to 4 from the pole, go around the circle all the way to 4 pi over 3 and make my point. And that is my Q. Groovy? All right. Hopefully you can still see it when it's little. All right, so now let's take a look. So I don't know how much you remember about polar coordinates, but just in case you forgot, you basically have something along these lines. Do a little quick and dirty review here. So if you have some ray that's been rotated, and suppose you've got this point X and Y right here. Okay, so you've got this point X and Y, and you can make a right triangle. So this part here would be R, and then you could drop down an altitude right here, and this distance would be Y. And then, of course, you have a theta, some kind of theta, which would be rotating counterclockwise. And then down in here, you've got your X distance, all right? So if you look at this trick-wise, cosine theta would equal to, awesome, X over R. And so that means that X equals R cosine theta. Now, Y, you would use the sine function, right? That kind of goes with Y. So sine Y is Y over R. And so Y equals R sine theta. Groovy? And then a couple of other useful tidbits to observe. R itself, do you see that R squared would equal to X squared plus Y squared? And tangent theta would be the ratio of those sides, Y over X. Groovy? All right, so looking at coordinate conversion, the polar coordinates r theta of a point are related to the rectangular coordinates x, y of the point as follows. So if you have polar and you want to go to rectangular, you use x equals r cosine theta and y equals r sine theta. If you want to go from rectangular to polar, you use tangent theta is y over x, and r squared equals x squared plus y squared. Cool, cool? All right, so let's take a look. Converting from polar coordinates to rectangular coordinates. So we'll plot the point in polar coordinates and find the rectangular coordinates for the point. So plotting 3 comma pi over 4. So again, we count out 3 and we go to pi over 4. So we have a point right here. And then converting this one, we're going from polar to rectangular. So we have x equals r, which is 3, times cosine theta, which is pi over 4. That's going to be equal to 3 times root 2 over 2. You don't have to rationalize if you don't want to. And then y is equal to 3 times sine theta, theta was pi over 4, which will yield the same result, 3 root 2 over 2. So the coordinate in rectangular form is 3 root 2 over 2, comma, 3 root 2 over 2. Cool, cool? Okay, looking at our second one, we have negative 2 5 pi over 3. So let's go ahead and rewrite that one so it's easier for us to deal with. So that's going to be equivalent to positive 2 and then 5 pi over 3 plus pi. So 5 pi over 3 plus pi is going to take us into quadrant 2. So we'll be coterminal with 2 pi over 3. Are we okay with that? Let's see. We'd first get 8 pi over 3, but then we'd recognize that that's coterminal with 2 pi over 3. Groovy? And so 2 was our r, and then we're going to 2 pi over 3, so we're about there. Now, getting this into rectangular coordinates, I'll use that last result. And so x would equal to r cosine theta, so 2 times cosine of 2 pi over 3. So x will be 2 times negative 1/2, which is negative 1. Y is equal to 2 times sine of theta, which is 2 pi over 3. So y is going to be 2 root 3 over 2, which is root 3. And so at the end of the day, our polar coordinates will be negative 2, 5 pi over 3 is equivalent to negative 1 root 3 in rectangular coordinates. And this one is the answer for that. All right, groovy? Okay, so now let's take a look at finding 2 corresponding polar coordinates for the point given in rectangular coordinates. So first we have to switch from rectangular to polar, and then we have to find an extra polar point. So, well, tangent at theta is equal to 1 over 0. So we're looking, because remember y over x, so we're looking at an angle where the slope is undefined, right? Or where the trig function is undefined. Where is x equal to 0? Well, at pi over 2, right? And at 3 pi over 2, but since we have 0, 1, I'm saying pi over 2, all right? So Now we need to find r. So r squared equals x squared plus y squared. So r squared equals 1. R will be 1. R is positive. So our first point could be 1 pi over 2. And we could do, what else do you want to do? We could do -1. If I add pi to pi over 2, I get 3 pi over 2. Those work for me. Groovy? Okay, so -2, 2. Recognize that you're in the second quadrant. So here, we're in quadrant 2. That'll be important for the angle, right? So we go to our tangent. Theta is equal to 2 over -2. Tangent theta is equal to -1. And so that occurs in quadrant 2 when theta is equal to 3 pi over 4. Now, r squared is equal to x squared, which was -2, plus y squared, which was 2. So r squared will be 4 plus 4 is 8, and so r will be 2 root 2. And so again, we'll just use 2 root 2, comma, 3 pi over 4. And another one would be, let's just do the negative again, -2 root 2. 3 pi over 4 plus pi is like doing 4 pi over 4. So that would be 7 pi over 4. Cool, cool? Awesome sauce. So hopefully you've seen this before, but if not, this will serve as a review. Now, graphing in polar form. So there are certain graphs that are good for you to learn. I'm illustrating some of them, and on the last page of this section, it shows like a bunch of them that you should be familiar with. So if r is always some number, right, and there's no angle, then you're just going to be tracing around that circle made by r. So here, if I take a look at x squared plus y squared equals r squared, I'm going to have x squared plus y squared equals -4 squared, which is x squared plus y squared equals 16. And this is the equation in rectangular form, and it happens to be a circle with radius of 4 and center at the origin. At 0, 0. So this one will be a real easy one to draw, right? So we'll go ahead and draw this one. Excellent. Perfect, perfect. Groovy? All right. So if you just have r equals something, you can ignore the negative. If it's negative, you can just consider the positive. You have a circle with that radius with center 0, 0. Now, if you only have theta equals something, we know that tangent theta equals y over x. We've also been given that theta is 5 pi over 6. So tangent of 5 pi over 6 is equal to y over x. And if I think unit circle thinking, I can think of this as the tangent at 5 pi over 6 would be, that's in the second quadrant, so the y value is positive, and it is 1/2. the x value is negative, and it's root 3 over 2. And that'll be my y over x. Groovy? So what'll happen is that putting that together into the point slope form of the equation of a line, I'll have y minus 1/2 is equal to the slope, which is that ratio. So if we cross out those 2's, we'll get negative 1 over root 3, and then x minus, a minus is plus, root 3 over 2. And this would be y minus 1/2 equals, if I multiply the negative 1 over root 3 through, I'll have negative 1 over root 3 minus 1/2. So when I add the half from the left side to both sides, I'll just get negative 1 over root 3. So when I take a look at that, the easy way to graph it is going to be using the fact that theta is always 5 pi over 6. So something that is useful to look at is that if theta is always 5 pi over 6, isn't it also going to be 11 pi over 6, right? So we just get a line that crosses through the pole when we have just the angle equals something. Groovy? Okay, so next up we have r equals 3 sine theta. So when you have something like this, usually you almost have y, don't you? I mean, if you multiplied both sides by r, on the left side we have r squared, and on the right side we would have 3 times r sine theta. And what is r sine theta? Awesome. R sine theta is y. So this would be r squared equals 3 times y, utilizing the fact that r sine theta is y. Now, what is r squared? R squared is x squared plus y squared is equal to 3y. And so r squared was x squared plus y squared. Groovy? Now, let's go ahead and complete the square, because this is going to be a circle. Do you see that? But it will have a different center than that earlier one we did. So x squared plus y squared minus 3y equals 0. I'm completing the square, so I divide negative 3 by 2, and I add that amount squared to both sides. So I'll get x squared plus the quantity y minus 3/2 squared equals 9/4, which is 3/2 squared. And so that's our equation. We're going to have a circle. So in general, when you have a sine theta, you're going to get a circle with radius. So if we think about r equals a sine theta, you're going to have a circle with radius a over 2 and center of 0 a over 2. So again, that's general. So for us, we will have a radius of 3/2, right? And center is at 0 3/2. So 0 3/2 will be about here. And then the circle, so if, you can always add in a couple points. We initially had r as 3 sine theta. So if theta was, I'm going to choose pi over 6 because I won't get a radical. So sine of pi over 6 is a half. And so we'll get 3 halves. R is equal to, what will that be? Yes, r would equal to 3 halves, comma, pi over 6. So, and then you'll have the same thing going on the other side. So what'll happen, and then when you've got pi over 2, you're going to be up at 3, okay? And when you're at 0, you're going to be at 0. Cool, cool? So your circle is going to look something like this. So when you have, a sine theta, it sits on top of that x-axis, intersects at the pole, and the radius is half of the coefficient to the sine function. Groovy? Okay, so now when you've got something like part D, it can be really useful to just switch everything in terms of sine and cosine. So let's start with that. We have r is equal to cosine theta over sine theta, converting the cotangent, times 1 over sine theta. So I'm kind of okay with the cotangent, but let's multiply both sides by sine theta, because then that's going to give us a y on the other side. Do you see that? So this one will divide out on the right side, and then we will have r times sine theta is equal to, I'm going to put it in terms of the cotangent theta. Now, r sine theta we said was y, and cotangent theta is x over y. Cool so far? All right, so we know we'll have a point at 0, 0, right? And then we'll also have, we can look at the original graph if you want to. I mean, if we look at, well, then we'll get into decimals. We know that we'll have a point at 1, 1, right? So remember, these concentric circles are just made using, your original axis, right? So we have a 1 here and a 1 over here. So it'll be about right here. And then you'll have symmetry down here, right? And so, that's the wrong one. It's about here. And so you'll have a parabola that looks something like this. Nope. Third time's a charm. And that's not perfect, but you get the idea, okay? Excellent. All right, so now when you're converting the rectangular equation to polar form, right, you just use the r cosine theta for x and r sine theta for y. So x squared will be r cosine theta squared, and then minus y squared, y in the purple, that's r times sine theta squared, is equal to 9. So we'll get r squared times cosine squared theta minus r squared times sine squared theta is equal to 9. Factoring out an r squared, we'll have cosine squared theta minus sine squared theta is equal to 9. And that's a double angle identity in here. So we'll have r squared times cosine 2 theta is equal to 9. And we're done. Cool, cool? All right, x times y is equal to 4. So again, you're going to have r cosine theta times r sine theta equals 4. So we'll get r squared times cosine theta times sine theta is equal to 4. You can either leave it like that, or you could multiply both sides by 2, because 2 times sine theta times cosine theta is sine 2 theta. So that would equal to 8. So we had 2 times cosine theta times sine theta was the sine 2 theta. Groovy? Okay, so now we have slope in polar form. All right. So apologies ahead of time. There is a typo here. Y is equal to r sine theta. Let's check out dy d theta. So that's just the product rule, right? So dy d theta would be r cosine theta plus dr d theta sine theta. And if you wrote it in terms of f at theta, you would have f at theta times cosine theta plus f prime at theta times sine theta. Cool, cool? And dx d theta would be, let's see, x is r cosine theta, so you'd have negative r sine theta because of the derivative of cosine theta. And then we would have plus dr d theta times cosine theta. In terms of f of theta, that would be negative f at theta times sine theta plus f prime at theta times cos theta. Cool, cool? And so kind of similarly to how we derived dy dx in the parametric form, you do the same thing here. And so we have dy dx, right, is equal to d dx of y, which in turn is equal to, if I separate that d dx because it's all multiplied, and then I put in a d theta over d theta, I end up with dy d theta, and then when I divide, I'll flip that d theta dx, and I'll get dx d theta. Cool, cool? And what did we find all that to be? So I'll write it here, dy dx is equal to dy d theta, which we found, remember, in the purple. I'll write this in terms of f of theta, and so this is f at theta times sine theta, times cosine theta, my bad, plus f prime at theta times sine theta, and that's over negative f of theta times sine theta plus f prime at theta times cosine theta. Cool, cool? Provided, of course, that dx d theta is not equal to 0 at f at theta, comma, theta. So just remember to make that connection that dy d theta was this numerator here, which we derived up here, and dx d theta is all of this, which is this. Groovy? Okay, so, I guess that means solutions of dy d theta equal to 0 yield horizontal tangents, and again, another typo, my bad, provided that dx d theta, this is a dx d theta, is not equal to 0. You don't want 0, and it's not horizontals. You don't want 0 over 0, right? That's indeterminate. Okay, and then similarly, solutions of dx d theta equal to 0 yield vertical tangents, provided that dy d theta is not equal to 0 at the same time. So this should be a y. All right, so if dy d theta equals 0 and dx d theta equals 0 simultaneously, then no conclusion can be drawn about tangent lines. All right? So, tangent lines at the pole. If f of alpha equals 0 and f prime of alpha is non-zero, then the line f at alpha equal to 0 is tangent at the pole to the graph of r equals f at theta. And so sometimes if there are tangents at the pole, we can use them for finding the limits of integration for area of polars. Okay, so we have an example. Just one, but it's long. So here we go. Slope in polar form. So we have r equals 2 times 1 minus sine theta. We're going to sketch the graph of the equation by hand. So I know you have a calculator. Normally you would use your calculator. I get it. But let's just do it a little bit old school so you get used to the system. So we have r and theta. Now, I'm thinking that this will complete in 2 pi, all right? And the other thing I'm noticing is that 1 minus sine theta is going to be bound between 0 and 2, right? And then you have that multiplier of 2. So we won't get any negative r values, which is nice, okay? So to do this, we want to plug in values for theta, all right? So when we plug in values for theta, let's start with theta equal to 0. That would be sine 0 is 0, so we just get 2. We good with that? And then I'll go with pi over 6. The reason I chose that is because sine of pi over 6 is a half, so we don't get a decimal. And that's going to give us 1 for the output. And then pi over 2 is going to be 1 minus 1 inside the parentheses, which is 0. And then 5 pi over 6, we'll get 1 again. Awesome. Going into pi, we'll have 2. 7 pi over 6. The sine function will be negative a half, so we'll have 1 plus a half, which is 3 halves, right? So we'll get 3 when we have 7 pi over 6. And then at 3 pi over 2, sine function is negative 1, so we'll get a 4 output. And then at 11 pi over 6, we'll get what? A negative a half for the sine function, so we'll get 3 again. Cool, cool? All right, so here we go. We can, the farthest this goes out is 4. That's within our range. So each of these units will be a radius of 1. And then sometimes it can be useful to kind of write in those angles, okay? So the ones that are more easy to see are pi over 6. This would be pi over 3, pi over 2, of course, 0. Pi over 4 is right in the middle of pi over 6 and pi over 3. All right, so that should give us enough to go on. So let's get started. So we have an ordered pair in polars of 2, 0. So we are right here. And then 1 pi over 6. So we go to 1, and then we travel that circle to pi over 6. And then we had 0 pi over 2. And then at 5 pi over 6, which is over here, we're back to 1. At pi, we're out at 2, so it looks like we're going to have some symmetry going on here. At 7 pi's over 6, we're out to 3. At 3 pi over 2, we were at 4. And at 11 pi's over 6, we were at 3. So this is a limacon, and it looks like a heart. Isn't that cute? So it's very, it's like uniformly continuous at its lower point here. And then it goes something like this. Sorry, I have a kind of a crack in my screen, so when I use the pencil, it gets a little funky sometimes. All right, so you got something like this, cute little heart. Cool, cool. That wasn't so bad to draw, was it? All right. All right, so that's a limacon has a lot of different variations. Some of them have a loop. In fact, while we're here, let's take a look. Limasomes. So we just drew this one. It's called a cardioid. It's heart-shaped. And it looks, we had the version where we had the sine function, right? So if you have a plus or minus b sine theta, it ends up being kind of more up and down, and it ends up being sideways if you have cosine theta. All right, so when you have a over b equal to 1, you get that heart shape. So a plus or minus b cosine theta. So if you look at ours, if we had multiplied this out, we would have had 2 minus 2 sine theta. So our a equals our b, which equals 1. If, and as time goes on, if you work with these a lot, you'll get used to this. If a over b is less than 1, you get a loop-de-loop inside, like that first one, this one here. If a over b is between 1 and 2, you get just a little dip. So it's not quite a heart. And then you get a really flat side here if a over b is greater than or equal to 2. So it almost looks circular. All right? And the names limosome with inner loop, cardioid, dimpled limosome, and convex limosome. All right? So here we go. Working with our limosome, we have our next challenge is to find dy dx. So r equals, I'm going to write it as 2 minus 2 sine theta. And so let's write this as f of theta. So f prime of theta is what? Beautiful. It's going to be negative 2 cosine theta. So remember that dy dx is equal to f at theta times cosine theta plus f prime of theta times sine theta. And we derive these above. This is just dy d theta. And then we have negative f at theta times sine theta plus f prime at theta times cosine theta. Cool? And so let's do this. We found f prime of theta. So now let's find out what dy d theta is, which is that numerator, all right, in terms of our graph. So dy, I think I did the dy, what did I do it before? I want to be consistent. I did it in purple. So we'll do this. Dy d theta is equal to f of theta, which is, I'm going to write it in its original form, which was, now I'll just write it as 2 minus 2 sine theta. And then times cosine theta. And then we had plus f prime of theta, which was negative 2 cosine theta times sine theta. And so if I simplify this one a bit, I'll have dy d theta is equal to 2 cosine theta minus 2 sine theta cosine theta minus 2 sine theta cosine theta. So dy d theta will be equal to 2 cosine theta minus 4 times sine theta cosine theta, because those are like terms. And so dy d theta, if I factor out a 2 cosine theta, I'll be left with 1 minus 2 sine theta. Now, dx d theta is going to be equal to 2 minus 2 sine theta times sine theta, and that was a negative, and then plus negative 2 cosine theta from f prime times cosine theta. So dx d theta, when I simplify, will be negative 2 plus, actually negative 2 sine theta very sloppy theta, my bad. And then we would have plus 2 sine squared theta minus 2 cosine squared theta. So I have a lot of sines here, so I'm going to get that cosine theta term into sines. So we'll have 2 sine squared theta minus 2 sine theta, and then changing that to negative 2 cosine squared theta, I'll have minus 2 times 1 minus sine squared theta. All right, so now we'll have dx d theta equals 2 sine squared theta minus 2 sine theta minus 2 plus 2 sine squared theta. For sine squared theta, minus 2 sine theta minus 2. So I can factor out a 2 and then factor the remaining terms. So I'll have 2 times 2 sine squared theta minus sine theta minus 1. And that's going to factor as 2 times 2 sine theta. And I need the negative to be in front of the sine theta, so it'll factor like this. Groovy? Okay, so now that it's all simplified, it shouldn't be that awful to deal with here. So dy dx will be equal to, so dy d theta ended up being 2 cosine theta times 1 minus 2 sine theta, and then dx d theta ended up being 2 times 2 sine theta plus 1 times sine theta minus 1. And I can divide out that 2, and so dy dx, and let's see, I can factor out something else. Dy dx, 1 minus 2 sine theta and 2 sine theta plus 1 divide out to be negative 1. So dy dx will end up being negative cosine theta over sine theta minus 1. Oops, I think I copied that wrong, didn't I? No, I'm good. Over sine theta minus 1. Cool so far? All right. Now, find all points, if any, of horizontal and vertical tangency. So horizontal tangency is when dy d theta is equal to 0. As long as dx d theta doesn't also equal 0. So dy d theta, setting that equal to 0, we had 2 cosine theta times 1 minus 2 sine theta. So either 2 cosine theta is 0, or 1 minus 2 sine theta is 0. I don't need the parentheses, sorry. So this would be cosine theta is 0. Theta would be pi over 2, or 3 pi over 2. Or one equals 2 sine theta, which leads us to sine theta is 1/2. And that happens when theta is pi over 6 and 7 pi, no, not 7 pi, my bad, 5 pi over 6. So in those first two quadrants. And so we already have the matching values because we found those. Remember when we were doing the points? So at pi over 6 and 7 pi over 6, r is 1. And at 7 pi over 6, r is 3 from our graph. So there's horizontal tangents at let's start with the pi over 6's. So we know 1 pi over 6 since we were talking about them. We also have 3, 5 pi over 6. Now, looking at the graph, you're really going to be, this is a sharp corner right at the heart. So when I say this, I'm looking right here. And so it's not going to have horizontal tangency, but down here we will. So at 3 pi over 2 we will, but not at pi over 2. So we'll have one at 4, 3 pi over 2. Cool so far? All right, vertical tangency. We'll look at our simplified dx d theta and set it equal to 0. So 0 will equal to 2 times 2 sine theta plus 1 times sine theta minus 1. And so the 2 obviously is not the 0 factor. So we'll set 2 sine theta plus 1 equal to 0, or sine theta minus 1 could be 0. So sine theta would be negative 1/2, or sine theta would be 1. So on this left-hand side, theta would be at 7 pi over 6 and 11 pi over 6. And over here, we would get theta is pi over 2. And if we look at the graph, we can certainly see, sorry about my dogs, that would be true. And so we will have vertical tangents at All right, so let's see what we got for our output values. We had 3, 7 pi over 6, 3, 11 pi over 6, and then at pi over 2 we had 0. So 0 pi over 2, 3, 7 pi over 6, and 3, 11 pi over 6. Cool, cool? All right, and finally, we have tangents at the pole. So this was the one where we needed to find out when f of theta was equal to 0, and that would be a special number, and then we would have to check to see if the derivative evaluated at that number was non-zero. So remember that f of theta originally started out as, what was it? 2 times 1 minus sine theta, right? So 0 equals 2 times 1 minus sine theta. Well, 2 is not the 0 factor, so let's look at 1 minus sine theta is 0. Sine theta would be 1, because you would have got negative sine theta is negative 1, and then you would have multiplied by the negative. And then theta is pi over 2, which makes it the alpha that they're talking about in the theorem. Then you come over here and you say, okay, is f prime of the alpha, is that equal to something that is non-zero? So f prime at theta, we know, is negative 2 cosine theta. And our alpha is pi over 2. And so f prime at alpha, do you see, is 0. So because f prime at alpha is 0, there's no tangents at the pole. If f prime at pi over 2 had been something else that wasn't 0, then there would have been. And you can see that looking at the graph, right? You can see the pole, and there's no tangents at the pole. Cool, cool? All right, so here are the graphs, common polar graphs that you might want to know. We talked already about the limasones. The rose curves you get when it's not going to have a constant that is adding or subtracting the trig function. It's just going to be the trig function with a multiple angle. All right, so when they're odd, you get, so if you have an odd multiplier to your angle, then you get that many petals. If you have an even multiplier to your angle, you get double the amount of petals. And the length of the petal is your multiplier to the trig function, your a. Cool, cool? Okay. Circles, we talked about those a bit. We already saw an example of a sine theta, right? Now, a cosine theta, it touches the, instead of sitting on top of the x-axis, it's stuck to the side of the y-axis. And so it has the same properties where it's got a radius of a over 2, but it completes itself from negative pi over 2 to pi over 2, whereas the other one completes itself from 0 to pi. Now, these infinity graphs are really groovy. They're when you have like a double angle, right? And then you have r is squared. So you have r squared equals a squared sine 2 theta. It's called a lemniscate, I'm sorry, I don't know. And your A is measured through that point, that part that cuts one of the infinity deals in half. So that's kind of cool. Instead of getting an infinity tattoo, you could just get r squared equals a squared cosine 2 theta. All right, anyway, that wraps it up for this section. We'll be covering 10.5 next time. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hit that like button, the subscribe button, and share the video. Bye.